Welcome everybody to this H3D Foundation webinar. We're always pleased to have you. Thank you for joining us again and again every week, and more or less every week. This week we're thrilled to have an old friend of ours, Jihye Roh, who was with us at H3D in June and presented ASKCOS. And we were so excited by this platform, we just really wanted to share it with our broader network. Because we know it's going to add a lot of value to what we're all trying to do. So let me read Jihye's bio so that you have a sense of who she is, and then I'm going to hand over straight away so we can kind of get into it. Jihye Roh received her Bachelor's of Science in Chemical and Biological Engineering from Seoul National University in South Korea in 2022. She is now a fourth-year PhD student in chemical engineering at MIT, working in the Coley Research Group. Her research focuses on advancing computer-aided synthesis planning, with a particular emphasis on developing AI-driven methods to enable retrosynthetic analysis of complex molecules. She is a developer and maintainer of ASKCOS, an open-source software suite for synthesis planning, and collaborates actively with industrial partners in the pharmaceutical and biotechnology sectors. Jihye, thank you so much for doing this for us. We're really excited to have you, and I'll hand over straight away to you. Everyone, reminder, of course, that there'll be a Q&A at the end. Thank you so much.
Thanks, Nicholas. Thanks for the kind introduction, and thank you everyone for joining this webinar today. So today's webinar will be on ASKCOS, which is an open source data-driven synthesis planning software that we have been developing within MIT and especially within the Coley Research Group. And so today's webinar will focus on first providing an overview of the tools that are available in ASKCOS, focusing on the retrosynthetic analysis tools, and also introducing the additional forward prediction modules that are used for in silico evaluation of the proposed retrosynthesis. We also have additional utilities that I will go into share briefly in detail. And following this overview section, we will have a live demonstration of using the ASKCOS public graphical user interface that people can use for interactive synthesis planning. And so this is the slide that you have seen when you first joined this webinar, but ASKCOS is an open source software suite for computer-aided synthesis planning that offers a range of different functionalities to support chemists at every stage of the synthesis process. So as you can see here, there is a public web interface that is free to use, and it provides access to various functionalities, starting from retrosynthetic planning, reaction condition recommendation, reaction prediction, and more. And we also provide detailed documentation for how to use each of these modules. Additionally, since the code is open source, it's also possible for users to deploy ASKCOS either in the entire functionality or by deploying one or more of the individual models. Also, because the code is open source, ASKCOS is also very customizable within the specific deployment, where the super user who deployed ASKCOS can provide different datasets for reactions or building block molecules, and also train each model on the reactions in the internal datasets. These models can then be integrated into the specific deployment where people can access the models through their own web interface. So as I've mentioned, ASKCOS is a tool that is aimed to aid various aspects of synthesis planning, starting from generating retrosynthetic plans for a specific target and also evaluating the proposals in silico. ASKCOS has various models or modules for synthesis planning that is centered around retrosynthesis, as you can see here, starting with one-step retrosynthesis models, multi-step retrosynthesis algorithms, and also forward prediction modules available, as well as other chemistry utilities. I'll share more about each of these modules in detail in the upcoming slides. So starting with computer-aided retrosynthesis, which is a focus of the ASKCOS software, is that in computer-aided retrosynthesis, we aim to propose synthesis pathways for a target molecule. And so the way that data-driven models for retrosynthesis work is that given a target molecule, we have various different models that are aiming to predict the precursors of the target molecule, which can be used to synthesize the target molecule in one step or one pot type of reaction. And once we have these models are iteratively applied until we reach commercially available building blocks to propose full synthesis pathways for a target molecule. And so these one-step models or one-step data-driven models can be divided into template-based and template-free models, where the first class of models, the template-based models, aim to predict the likely templates that can be applied for a specific molecule. So here, templates are essentially reaction rules that can be encoded by chemists or extracted from reaction datasets using tools like RD-Chiral. And once we have this list of templates, which encode how a substructure in the product molecule is transformed into the substructure in the reactant molecule, then the goal of these models is to predict the most likely templates that can be applied for the target molecule. Once we have this predicted list of templates, they can be applied to the product to generate the reactant structures, as you can see here in the bottom. One of the benefits of these template-based models is that when these templates are extracted from reactions, then they can be traced back to the reaction references. This means that you can look up the specific conditions that these reference reactions were run under, and also look at the specific procedures that were used for running the reaction. However, these models are inherently limited by the scope of chemistry that's encoded in the templates, and there's always a trade-off between how detailed or how general you encode or write these templates. So if you're too specific, then a specific substructure is included in the template, making it hard for the models to learn how these rules generalize. And if you're too general, then it could propose chemically invalid predictions. And so template-free models are an alternative to template-based models where it doesn't rely on the use of these templates. And so these template-free models directly generate the reactant given the product structure. They can also be further classified into graph edit-based or translation-based methods, where graph edit-based methods represent molecules as graphs, where the nodes are the atoms and the edges are the bonds. And then these methods predict how these graph structures change from the product to the reactant. We also have translation-based models that translate the language of products into the language of reactants, where these use the natural language processing technology that we have and are developing. And so in these cases, molecules are generally represented in terms of SMILES, which is a string notation for molecules. And so in ASKCOS, we provide access to all of these different types of models, where we have the template relevance model, which is a template-based model, and we also provide access to template-free models. There's two different types of models that I won't go into too much detail here, but you can also read about the specific model types in this ASKCOS paper. We also have other modules that are more less of a machine learning model, but more of different ways to propose or predict different reactants. For example, we have template enumeration, which enumerates all of the templates in a given data set. We also have retrosym, which is a similarity-based method where you look up similar products in the data set and apply the templates from those reactions. We also have exact match, where you can look up exact products in the that were used in the literature. And so we'll share in the later part of the webinar, in the live demo, I'll share a little bit about how to use all of these models through the public web interface. We also have various data sets that were used to train each of these models. Some examples are the ReAccess dataset, which includes the journal and patent literature. USPTO is a dataset of reactions that were published in US patents. And Pistachio is a dataset of US and European reactions. We also have enzymatic specific reactions available for people who are interested in biosynthesis planning. So we have BKMS, which is a dataset of enzymatic reactions. We also provide a subset of the reactions that are in the ReAccess dataset that are specific to enzymatic reactions. One thing to note here is that ASKCOS is also customizable with internal datasets using the reactions that are in electronic lab notebooks at specific companies or in specific groups. So moving on to multi-step retrosynthesis, in the interactive path planning page, users can click on specific molecules to apply models to specific molecules of interest. In the multi-step retrosynthesis algorithm, we have computers that essentially select the specific molecules of interest until a full pathway is proposed. So this is typically formulated as a tree search problem. We're given a search tree of molecules and reactions. The algorithm selects the specific node to look at, and then expands this node, which means that it applies the one-step model to it, which gives the predicted reactants and reactions. And then the scores of the relevant nodes in the tree are updated, and this process is performed iteratively until some sort of stopping criteria is met. This could be, for example, finding pathways that start from building blocks. You can also set a limit on how long you run this search for, etc. And so in ASKCOS, we have the tree builder, which automates this process of synthesis planning. And so, for example, if you give in this target molecule, it will propose all of these different pathways that can be used to synthesize the target molecule of interest. And so there's various other versions or customizable features here where you can select the type of algorithm that is used. Here, MCTS and RetroStar are the two different versions that we provide. You can also select which of the models you would like to use for this automated synthesis planning. You can also change the what you would consider as a starting material. For example, you can provide the list of building blocks that you would consider as a starting material, and also provide a list of rules for the building blocks. For example, the building blocks that we provide in ASKCOS also have an estimate of the price, and so you can set a limit on the cost of the precursor. You can also set a limit on how the synthetic accessibility score of these molecules. So for example, you would want the tree to stop at molecules that are very synthetically accessible. You can also customize other settings, such as the number of carbon atoms, and etc. And other parameters, such as time, depth, iterations, or more, where here iterations are referring to the number of times that you apply the one-step model. And so these are search parameters that you can select and customize in the web interface. Once you have a list of these pathways that are proposed, the Tree Explorer provides a way of sorting through these pathways and ranking them based on various metrics. So some of the metrics that we provide here for ranking are depth, which is the length of the longest linear pathway, the number of reactions that are involved in the longest linear pathway. You can also sort by the total number of reactions. And plausibility here is a fast filter score that aims to evaluate how plausible this reaction is likely to happen in the lab. It's just a rough proxy. You can also use the score that is assigned to each reaction by the model, and other metrics like precursor cost, number of analogs, overall atom economy, and average PMI. Here, the number of analogs is an estimate of the number of synthetic analogs that can be generated using the same chemistry or template with a different building block. And overall atom economy and average PMI is more of a process chemistry centered metric that we provide, where in the case of average PMI, we use the top and predicted reaction conditions to calculate the value. And we'll talk a little bit more about the forward prediction or reaction condition recommendation tools in the later slides. And so this brings us to the forward prediction models. The first class of forward prediction modules is the reaction condition recommendation, where we have models that predict the temperature, catalysts, solvents, reagents, etc. And so in the first version of models that we provide, these models were aiming to predict the identities of these like catalysts, solvents, and reagents. We've very recently added a new model that predicts the amount of these agents in addition to their identities. For example, for how much of the specific catalyst or solvents would be used, and also how much of the reactants should be used for each of the reaction. Other types of reaction outcome prediction modules include predicting major product prediction. In these cases, you can provide the reactant and the specific solvents, reagents, etc. that will be used in the reaction and predict the major product. Plausibility is what I've mentioned before, where it aims to predict or roughly estimate the likelihood of a success of a reaction. We also have models that predict the impurities of a reaction, where some specific modes of impurities that we're predicting currently include predicting the minor products of overreaction, dimerization, solvent addict, and subsets of reactants. So these are products that can be formed with different different sets of reactants given the specific reaction of interest. We also have models for predicting the selectivity of reaction. And so these tools can also be accessed through the public web interface in the forward prediction. These screenshots are a little bit small, so I will show a little bit more on the live demonstration portion. And so we can have these pages for reaction condition recommendation, where you see the amounts of reagents in the bottom, or reactants and reagents in the bottom. And you can also use the reaction outcome prediction page, where you predict the likely products, impurities, and etc. We also provide additional utilities that are aiming to aid this process of synthesis planning. One of the main utilities that we provide is solubility prediction, where it predicts the solubility of neutral organic molecules in specific solvents of interest. We also provide two different models currently and are working in process of adding a new model. But the difference between these two models is that SolProp is a model that uses thermodynamic properties to predict solubility, where FastSolve is a model that's trained directly on solubility values, so it's trained to directly predict solubility. And so as you can see here, once you enter the solute and the solvent and the temperature value, it would give you a table of the solubility values that are predicted for a specific combination. Another utilities that we provide is the QM descriptor, which aims to predict different molecule or atom and bond level descriptors for a specific molecule. And so these models are trained on different QM descriptors that were computed using DFT and now are trained to predict these values. Some of the molecule level descriptors that are predicted here include the dipole moment, HOMO-LUMO values, as well as specific atom and bond type descriptors, which include orbital occupancy or bond and length and charge. And so here in the QM descriptor page, we have a way of looking at the 3D visualization of a molecule where you can click on specific atoms to look at the atom level descriptors as well. We also provide a lot more descriptors here, which are too many to name on this slide. So I'd encourage going into the page and looking into the specific types of values that are predicted. Lastly, the last set of utilities that we provide is molecular complexity. So we offer various structural and synthetic complexity values that you can compute using the specific molecules that are interested. Some structural complexity values of interest, or the structural complexity values that we provide are Bird's complexity score, Blotcher's scores. There's many more. We also provide access to synthetic complexity, which aims to predict or evaluate how synthetically complex or how hard these molecules are to make in the lab. And so the specific metrics that we provide are SA score and SC score. With that was a very high-level overview of the functionalities and modules that we have in ASKCOS. For those of you who are interested in learning more about how to get started with ASKCOS, ASKCOS Docs or ASKCOS Wiki is a nice page to get started. It offers detailed documentation on using the public website, customizing the different settings that are available, as well as deploying a custom version of ASKCOS and adding different modules, models, etc. I would like to mention that ASKCOS is a tool that aims to assist chemists. So ASKCOS has a lot of data-driven models that are available to help chemists in their synthesis planning process. However, data-driven models are heavily influenced by the data that they are trained on. And so if you go on the public site and try out different models that are available, you will see that the model predictions vary based on the type of data sets that they are trained on. And so I would recommend exploring the different types of data sets, as well as if you have specific interests or specific types of chemistry that you're interested in, training a new model based on a subset of data sets that are specific to those reactions might be of interest. The models themselves don't also understand chemistry the way that chemists do, and aside from what has been encoded into the formulation, their understanding of chemistry is very different from how a human would understand chemistry. Because of that, we encourage further evaluation of the proposals, for example, by doing a similarity search in other softwares such as SciFinder or Reaxys. ASKCOS also offers API access with auto-generated docs for people who are interested in integrating ASKCOS in a more automated workflow. And so you can access these APIs through Python or command line interface as well. And so ASKCOS is currently actively being developed and supported. So we have a lot of people who've contributed to all of the functionalities in ASKCOS. And we also have this ASKCOS team currently working on developing and maintaining ASKCOS, as well as other members of the Coley Research Group and the MLP Consortium, which are working to always add new tools to ASKCOS as well. And these are all of our sponsors and data providers, and yes, as well. And so with that, I would like to end the first portion of the webinar and move on to the second section, which is a live demonstration on how to use the ASKCOS web interface. So here I am sharing the ASKCOS public web interface. This is the first slide or first page that you will see when you access askcos.mit.edu. And so here you can start by entering the SMILE string of the molecule that are of interest. For example, a SMILE string will look like this, where you can just Google the name of the chemical that you're interested in, PubChem, for example, and copy the SMILE string of a molecule. We also provide a name resolver, where if you click on this button on the left and type in the name of a chemical and click resolve, This will populate or this will give you the small string of the molecule that you are interested in. Once you enter the molecule, it will show you all of the functions that are available for this molecule. And so some of the predictions are, for example, predicting the SC score, which is the synthetic complexity score, as well as predicting different types of forward prediction modules. But here I would like to start with the interactive path planner, which is our centralized location where you can run one-step retrosynthesis analysis. So once you enter this interactive path planning page, the target will be populated with the specific smiles that you've entered in the first page. You can also always replace this target with specific molecules of interest. We also offer a way of drawing the molecule where it would give you the smiles of the molecule that you've drawn. One of the main things to change here would be the strategy settings. So here, let's reset. And this will show you the default settings that are available for ASKCOS. And the main setting to change would be the strategy plan. And this is the specific model that is used to generate the predictions. The default setting here is the template relevance model, which is the template-based model that I've shared previously. And this model is specifically trained on the Reaxis dataset. If you're interested in other models, or other datasets, you can click on the template set and change the specific model. Let's use the pistachio model for this demonstration. You can also mix different strategies. For example, you can add a second model by just clicking on this plus button, which will add the second strategy. And you can also change the different types of models that are available. The augmented transformer and graph to smiles are the template-free models, and we also provide access to exact match, retrosim, and template enumeration that I've shared in the previous part. So for this demonstration, I'll click on the augmented transformer using the USPTO dataset, and we can also add a third strategy that uses retrosim and BKMS. You can also change the threshold, which is the threshold value for the similarity, and save the settings here. And so once you save these settings, you can click on one step, which will run the model to give you the predictions. And so once the models are done running, it will populate this canvas with the predictions, where you can scroll or click on these specific nodes to see all of the details about specific reactions that are proposed. For example, if you click on reaction node 1 here, this is a reaction that is predicted by the augmented transformer that is trained on the USPTO full model, and then you can also see the scores and the ranks of this prediction. If you click on the second reaction, this reaction was predicted by the template relevance model trained on the pistachio dataset. One thing to highlight here is that because it's trained, it's a template relevance model that uses these reaction templates, you can click on all of these links to access the reference details. So if you click the template link, this will bring you to the template information page, where it shows you the specific template that was used to give this prediction. And it will include this reference page, and the references for different data sets are different. But for a specifically pistachio dataset, if you click on this reference link, this will bring you to the patent page of where the reference was, the reference reaction was extracted from. And so here, going back to the reference page, the first part of the reference here for pistachio datasets are the patent ID, and then the ones in the brackets are the paragraph numbers. So you can also take a look at the specific paragraph that this reaction was extracted from. And now going back to the interactive path planning page, there's only 5 reactions that are added to this canvas by default, which is a setting that you can change. But if you're also interested in looking at different predictions in addition to these 5 types, you can click on the molecule node that has been expanded and scroll through all of these predictions that were given. So the top 5 were added by default, but you can also just add new predictions as well by clicking on this plus button. And then so once you've clicked and added a new node, this will give you the new reaction here, where you can also click on the specific reaction node and scroll through the details. For retrosim, which is a similarity-based method that looks up similar reactions or similar products and the reactions that these products are involved in, these methods also provide links to the references where you can click on the link, which will bring you to this BKMS site where you can look at the specific reactions of interest. You can also further expand this tree by clicking on specific nodes. So if you double click on a node, it will apply the model to those nodes again. Also, in these node details page of reactions, you can also evaluate these reactions further, which will bring you to the forward prediction page with the reactants and products pre-populated. For example, this will bring you to the condition recommendation page that predicts the solvents, reagents, catalysts, etc. You can also change the different types of models where version 2 predicts the quantities. You can also use the product prediction page to predict the likely products that can be formed, as well as predicting impurities or retroactivities. I won't go into too much detail in the interest of time, but all of these modules can also be accessed through the sidebar on the left, where we have models for retrosynthesis, models for forward synthesis, as well as other utilities like the solubility prediction page. Here, when you enter the solute and the solvent and temperature pair and select the specific model to use, then it will predict the solubilities for these values. We also have these QM descriptor page and molecular complexity page that I've mentioned in the webinar in the first section, and this will allow you to use all of the different functionalities that we have in ASKCOS. So this here, ASKCOS Wiki, is the documentation page that I've shared previously. And there are other functions such as looking at my results. So if you go back to this interactive path planner page, you can save your network that you've generated either into your computer as a JSON format or through your account and access the saved results through my results page. Another important feature is this build tree, which is the automated tree builder that I've mentioned previously. So once you click build tree, this will submit the tree builder job, which runs in the background. And then once the job is done running, you will see a pop-up here that says the tree builder job is completed. In the strategy settings page, there's also various settings for the tree builder that can be customized, such as the tree builder version, the time you allow the search to run, as well as selecting the specific terminal chemical criteria, such as selecting the source for the building blocks, or setting a price limit on the specific building blocks, or what you would consider a building block. There's a lot more settings on this page that I'd encourage looking into ASKCOS Wiki to see more details. And so with there was a pop-up here that says the tree builder job is complete. And once you see the pop-up, you can click on view results there directly or click on my results. And so this will show you the results of the tree builder here. And so here, this is the completed tree builder job that was run. And so you can see the different trees in 2 different ways. Through view trees, which will bring you to the tree explorer page where you can scroll through the different types of pathways. You can also go back to, go back to my results and click view in IPP, which will populate this interactive path planner canvas with all of the pathways that were generated. And so you can also click on specific nodes of interest and look at the details in a similar way as previously done. And so this was a very short overview of using the public interface for retrosynthetic planning and also for forward prediction. But in the interest of time, I would like to stop the live demonstration here, and I'll be happy to take any questions.